So consider the drone. When we talked about the accelerometer, we said accelerometer is a set of three sensors that allowed me to detect movement and forces and the roll and the pitch. But yaw, no. In order to have the yaw, we need either a gyro for a short period of time where the drift is neglectable, or if we're looking on a long period of time, we need some sort of a global sensor, an extra sensor, which is the compass. So a compass, everybody can think of a compass, is a way as a sensor that actually detects magnetic field. We have it in our phone. So let me go back to the demonstration. So we see here the sensor that looks like the icon of a magnet. Often the magnetic sensor in the phone, or the e-compass, is referred as a magnetometer, or a 3-axis magnetometer. Let's demonstrate. So I'm holding my phone horizontally, and I put it on the table. Let's put metal things aside. Now I move it more or less towards north, and I see the green line going upwards. Let's push it to the south, and the same thing happened with the green line. It goes to the negative value. So a sensor here would detect the force on a negative direction, and the same sensor on that manner would detect the magnetic force of Earth in a positive axis that way. Now, it's quite complicated, but the way to understand that is through understanding the gravity. So a gravity is a force going downward. A magnetic field of Earth is going, instead of that way, that way. We are in Israel. It's about in the northern hemisphere, about 32 degrees above the equator. So the magnetic field of Earth is not going north, but into the Earth. Well, it's quite complicated because we are used to think of gravity as downwards, and we are relative people, so we understand that. But with the magnetic field, it gets a little shady, and so in order to keep it simple, I want you to think as following. In any area, large area, there might be different properties of magnetic field of the Earth. But smart people in NASA and other agencies have measured it to an extreme accuracy. And knowing that you are, say, in Israel or in the center of Israel, then there is this relatively accurate vector or known vector of the magnetic force that the sensor can detect. Knowing that, so instead of gravity, let me use that, instead of gravity going downwards, we have magnetic field going there. Now, if I have my three sensors, magnetometer sensors, maybe the sensor positioned that way is kind of agnostic to the magnetic field because it can only detect things in that linear one dimension. And that one, just a little bit. But the third one is being, say, pushed or detect this magnetic field. Now, in order to demonstrate that, I would take a phone. I'm not moving that phone, but a phone has a speaker with some magnets and so on. And when I'm playing with it, you can see a huge change in the sensors. So again, this phone is not moving too much. I'm taking another magnetic or a metal device, and I'm having it close to the my sensor, and you can see those mistakes. So keep in mind that say a drone, if you put some magnet nearby its sensor, it might get crazy. Or those people who have those those phones, those fancy phone covers with a tiny little magnets which are relatively strong, or some people have, my wife has this magnet here, and it's for like a smartphone holder in the car. So that magnet actually may ruin the ability of the sensor to detect the north. Now, some people might not care about it, but if you are a drone or if you are a real drone and you care about navigating and maybe a GPS is not valid, then knowing the north or knowing the way your sensors should be calibrated is extremely important. And all the people I'm sure that has been flying and playing with drones often gets this pop-up on their app when they fly the drone that says, oh, your compass need to be calibrated. Meaning, maybe those motors, well, not maybe, they are magnetic. And having a sensor which is so sensitive and strong magnets in a very close proximity to it might have it, confused. Other smart people, actually extremely smart people, engineers, have come up with an extremely simple solution to that. In any, even a toy-grade drone, there are this set of sensors which, in a way, can detect those interference and overcome them. I want to summarize. Those three MEMS sensors, accelerometer, gyro, and magnetometers, are usually combined in the same chip. It's micromechanics. It's an extremely small chip. You may go to Google, say, MEMS IMU or MEMS sensors, and look for images. You would see those amazing silicon sensors, and everything is mechanics, those tiny springs made of silicons. And I know very little about them, but how they actually being manufactured to the price of a few cents, and they work amazingly. But those are extremely important sensors. They allow this drone to fly, to navigate. They allow my sensors in the car to either open the airbags when there's a serious accident, or not doing that when I'm just bumping into, I don't know, or just backing up and touching the bumper of my wife's car. She hates when I'm doing it, but I do. Combining those three sensors, accelerometer, magnetometer, and gyro, towards a global accurate orientation in high sampling rate is, the topic of a lot of PhD theses and a lot of master students and a lot of companies. A few of them will be STMicro and Bosch, that each of them have their own tiny sensor with an algorithm that takes the information for all the sensors, or maybe multi-sensors, and output global orientation in high sampling rate. Some of them are, commercial off the shelf, inexpensive for gaming, and some others having this, are implemented in those drones or in the big rockets of Elon Musk or SpaceX that, they fly up, they do the maneuver, and they go backwards, and they do this seaside burn and being able to land on a drone ship in the middle of the Atlantics. It's an amazing piece of hardware which is commercial off the shelf. It's available for everybody, and you have it in your phone.